Hi everybody, my name is Mohammed Ibrahim, graduate student in Texas A&M Central Texas, and I'm majoring in mathematics. I would like to present to you some fact about Euler contribution to mathematics. Also, this presentation is prepared for the History of Math class at Texas A&M Central Texas. The presentation outline. First I will talk about Euler biography, secondly Euler and his long journey in mathematics, some Euler symbol and notation, and finally conclusion and some review question. Leonhard Euler was born in Basel, Switzerland on April 15, 1707. His interest in mathematics had certainly been sparked by his father teaching, and he took some freshman courses on elementary mathematics given by Johann Bernoulli, who encouraged him to study more advanced mathematics books on his own. In 1723, at the age of 16, Euler completed his master's degree in philosophy at the University of Basel. Moving to St. Petersburg in 1727, he went to St. Petersburg where he worked in the mathematics department with Daniel Bernoulli, his friend, and became in 1731 the head of this department. In 1741 he went to Berlin and worked in Berlin Academy for 25 years, and after that he returned back to St. Petersburg where he spent the rest of his life. In 1771 he became totally blind, but produced almost half of his work totally blind. In 1783 he passed away from brain hemorrhage. Euler left a wide range of knowledge in almost all areas of mathematics, like geometry, calculus, trigonometry, algebra, applied mathematics, number theory, as well as optics and other area of physics. And he's considered one of the most prolific mathematician in history, and the greatest and one of the greatest mathematician of all time. His accomplishment in geometry were revealed in two formula: the Euler line of a triangle and Euler polyhedron theorem. Euler line formula named in honor of Euler, and here he said if we take any triangle ABC, and if we draw the orthocenter point and the centroid and the circumcenter of this triangle, we all know how to draw that. The orthocenter, it's the point of intersection of all the three altitudes of this triangle ABC. Centroid, the point of intersection of all median of ABC. Circumcenter, if we draw the perpendicular line, for example, to AC, going through the middle of AC, and the same from AB, the perpendicular line which go through the middle of ABC, and connect all these three lines, will get the circumcenter. And actually the circumcenter is the point, the center of the circumscribed circle of ABC. So he claimed that these point lie on a straight line, and they are collinear, and the distance between the centroid and the circumcenter is equal the half distance between the centroid and the orthocenter. And these relative distances between these points don't change when you vary the shape of the triangle, and that's what really makes Euler line so famous. Talking about the Euler polyhedron theorem, what does this formula here tell us? Look at a polyhedron, like for example a cube or tetrahedron here on this side. Count the number of vertices. For example, for a cube we have 8 vertices, 1 2 3 4 in the top and 4 in the bottom. And next, count the number of edges of these polyhedron. In the cube, for example, we have 12 edges. 1 2 3 4 5 6 7 8 9 10 11 12. And we have also, finally if we count the number of faces, we get 6. Now if you have the number of vertices minus the number of edges plus the number of faces, we'll get 2. And actually if we plug these number, we get 8 minus 12, that 4. 8 minus 12, we get minus 4, plus 6, it's 2. And we can try it also for the tetrahedron. We have 4 vertices, 6 edges, 3 in the bottom, 4 5 6 and 4 faces, 1 2 3 in the base and 4 in the other side. And if we plug these number in the formula here, we get 4 minus 6 minus 2 plus 4, we get 2 as we expected. And that little formula turned out working for every pretty much every polyhedron except the one which have a hole running through him. Also, Euler was interested in number theory and was inspired by Goldbach, and he went through Fermat number theory. He organized Fermat work and found proof for most of the claim Fermat made. So let's show some Euler theorem in that area. He showed the phi of n. What does that mean? That mean the set which contain the integer number relatively prime to n. Like for example, phi of phi is equal to 1 2 3 4. Those are the integer number relatively prime to 5. And he proved some other small theorem related to this formula here. Like if n is prime, then phi of n equal to n minus 1. For example, phi of 7 equal to 7 minus 1 equals 6, and actually phi of 7 equal 1 2 3 4 5 6. So we have 6 integer relatively prime to 7. And he showed that if n is a product of 2 prime, p and q, then a phi of n equal to p minus 1 multiplied by q minus 1. For example, phi of 15 equal to 5 of 3 multiplied by 5. Those are 2 prime number. Then we can compute the phi of 3 multiplied by 5, which equal to phi of 3 multiplied by 5 of 5, which equal to 3 minus 1 multiplied by 5 minus 1 equal to 8. Also, he showed that if GCD of an equal to 1, that means a and n are relatively prime to each other, like 5 and 2, then a to the phi of n mod n equal to 1. In our example, 5 to the power 5 phi of 2, which is 1, phi mod 2 equal to 1. And in general, he show for any number n, if n is equal to the multiplicative product of prime number like p1, p2, p3, and etc., we can compute the phi of n, which will be equal to n multiplied by 1 minus 1 over p1 multiplied by 1 minus 1 over p2, and etc. And basically all these formula we can prove using, you know, some show some couple example and figure out the pattern behind this formula, and then we can generate easily the formula Euler proved. Next, he came up with an identity formula to describe the relation between the exponential function of a complex number to trigonometric function EIX equal to cosine x plus I sine x. And here's some picture for this function, how it look like. Here we can draw the real part of this function, which is equal to cosine x, and in the second picture I have drawn the graph of the imaginary part of the function, and here that's represent the 3D graph of the e to the power ix function. And here this function, it's the same but it's more detailed. Also we can draw this function using the complex plane, the unitary circle here, the imaginary x and the real x, and we can draw the EIX function. Euler gave 3 proofs to prove this formula, and here one of the simple proof. If we take t equal to cosine x plus I sine x and then calculate the derivative of this equation, dt over dx, we'll get I multiplied by I sine x plus cosine x, which is equal to it, and then we have the dt over t equal to I dx. Integrate both sides, we'll get log natural log of t equal to ix plus c. Now we need to calculate the constancy. If we take a special case, if we take x equal to 0 and plug it in the first equation here, we get t equal to cosine 0, which is 1, plus 0, I sine 0, 0. We'll get t equal to 1. Then plug the t in this equation here. Log will have log of 1 equal to 0 because of x plus c, so we end up with c equal to 0. And after that we'll get log of t equal to ix, and we can plug the what's t equal to, like t equal to cosine x plus I sine x. We'll plug it in this equation and we get the answer.